To see you all. We have a last day of my lecture here. Thank you all for sticking around. Today, it's going to be a little bit like lighter in some sense in that no slides. And I will briefly finish up yesterday's exercise. I just want to show a couple of more things. You don't have to do anything. And then I'm going to start this HealPix thing today. Yes, debugging my erroneous, Mariana, exactly. Like I said, I'm not ashamed to admit that's what happened. But I will maybe let me see if there are any questions from yesterday. Let's do this very briefly. Maybe speak up if you have a question. And if it's out of the scope, I'll say we can discuss later. But any questions about MCMC and supernova? We discussed the covariance matrix a lot on Slack. And as you may or may not speak, I will start sharing my screen, but feel free to. Okay, well, if not, I will. Yes, I got the right file. So I'm going to exercise 3. So you should all be able to see my Python screen. This is yesterday's exercise, except I have the solutions version, which I didn't ask Tiago to post, but it should be posted soon. And let's see, hopefully it's a bit bigger. So, okay, so this is that intro part. I guess I will, I guess I'll try to do this to do it again and run all the, I will run all of these again. So I will run all, let me see if it obeys me. Okay, so yeah, I think it'll be work. So I have to click this a little. And so these are all being executed and running. And this one also wants my input for the 2 data files. So remember, we were analyzing supernova data and we got somewhere, we got quite far. We had omega matter and omega lambda in script m. Okay, these are the parameters. That was a big message. And some middle of the road theory that we guessed was actually looked by eye like a great fit to the data. But this plot was a little bit hard because the axes were, the y-axis was stretched. So chi-squared of that model was very good. It was 43 for 40 data points. So that's a very good fit. Then we had likelihood and log likelihood. This was our log likelihood. And then we had a sampling algorithm, stepping, and it's still running here. I'm running it for 10,000 steps, and it's just finished them now, and acceptance rate is 0.2. So remember, this was our Metropolis Hastings algorithm. There are 3 parameters. We start at some point. We have to define some arrays, the chains array of parameter values and the log likelihood array. The weights are going to be key in a moment, but let me just say I go through n steps and each one may be rejected or accepted. I print out every 1,000. Then here, I propose to step to a point Q, and I calculate likelihood at that point Q. If that likelihood is bigger than the one I'm at now, I move. But if it's smaller, I still move if I satisfy that random number condition. So I draw a random number. So if accepted, I move and update the likelihood and say, yeah, accepts by 1. And also create a new weights array. This is basically adding an element to the weight array. So I create a new model. I say the new model parameters are these, and the new model weight I set to 1. But if I'm rejected, I don't do anything except increase weights at the old model. So for example, if I'm being rejected by a lot of time, I have a lot of weight there. That means I'm in a pretty good spot because my moves everywhere else are getting rejected. And likewise, if I'm immediately accepted, that's only going to be the minimal number that the weight can be is 1 if you immediately move on to the next point. And that's that. You wrap up acceptance rate. We looked at these trace plots, and we decided these look pretty good. And we saw if you have very bad stepping, it's still correct mathematically, but you're just doing things very inefficiently. Your acceptance rate is too slow. You're not moving anywhere. If it's too high, you're moving all the time, but you are crawling too slowly in your parameter space. Okay, so this is how far we've gotten. I think I previously had a typo here. And this is the kind of typos that you'll have a lot of if you just try to do this real time. So plot the chain So this is omega matter, the 0th column, and the first column is omega lambda. The column number 2 is script m. I usually don't care about script m. So I plot a log likelihood of models, and these are all the models. This is presumably 10,000 points. These are omega matter, omega lambda plane. This is a log likelihood. Let's see if it makes sense. These are numbers like minus 20. Does it make sense? Well, remember, log likelihood was this thing right. I have to scroll back up a lot. This was a log likelihood, and I was ignoring that other part, right? This part. So it's like minus 1/2 of chi squared. This is chi squared. It's minus 1/2 here of chi squared. Because chi squared is about 40 at the best model. Minus 1/2 of that is minus 20. And indeed, these likelihoods are minus 20 at best, and they can get more negative. More negative means that chi squared is higher. So for example, if chi squared is 100 or 200, then minus 1/2 log likelihood is like minus, I don't know, 40, 50, here, minus 28. So these are, so this makes sense that this, you always want to do this kind of sanity check. This number is minus 20. Okay. Now, let me look at the chat first before the punchline. It doesn't matter, Reggie, too much where you start MCMC. There are some rules that you shouldn't, that doesn't matter super too much. What does matter is how you're stepping, and I'm going to talk about that next. That is a much more important thing. The meaning of the weights, yes, I'll remind you once again. I just talked about them, but I can remind you once again. In fact, that's okay. And somebody is suggesting helpful installation things. Yeah, so this is kind of tough. You haven't installed it already a bit earlier today. Maybe you could just, well, okay, whatever, you can follow along. So here's my first punchline. This is not the plot you want. This is absolutely not the plot you want for the result. This is not your result. You don't put any contour around these points. These are your likelihoods. But really, you've been exploring the likelihood, you've been seeking. What you want is those weights. And weights is a number. Remember, if you are here and you propose a step, your weight is 1 at any model to start with. If you propose a step, if you move on, that weight is 1 and stays registered at 1 forever at the old model. But if you're rejected, the weight becomes 2. Then say you're back. So you start stepping, you're rejected, that weight is 3. You're rejected, that weight is 4. You accepted, okay, that weight is 4, remember it, move to the new model, initiate its weight as 1. So the weight is just the amount of time, the amount of steps you stuck around, you were around at any given model. And the weight is what you want. That's not the likelihood, okay? So this is not what you want, this plot. This is why I had to keep track of weights here. This is just telling you, it's walking in the area of parameters where I think it should be walking, right? Omega matter is about right, omega lambda is about right. Yeah, if you get these to be crazy values, if omega matter is, I don't know, 0.7 or 2 or something, that, you know, something went wrong. It's generally sticking around where you suspect it should, but that likelihood is not. You want, so let's just see again, weights here, this is a key line, I'm increasing with weight by 1 if I'm rejected. And the rest is just bookkeeping. Here, I'm just creating, you know, if I'm accepted, then that weight is done. And then there's a new model for whose parameters I remember. So remember in my lecture notes, I had a table where I have a column of weights and then 3 columns of parameters. And each row is a model. I hope that's a crucial information here. All right. So I want weights. So I have these weights. I kind of worked hard early in the day of my lecture to just to get this weights array not to be the wrong size or not the wrong shape. And it's just bookkeeping. Okay, there's no physics there. But now I plot weights. I plot the parameters corresponding to some weight. So this is omega matter, the 0 column. This is omega lambda, this column. And I have a color bar as the weight. So now the same as likely, but I have a color bar of weights. So you can see, remember, the weights, the smallest they can be is 1. No weight is smaller than 1. And we don't know what the highest weight is. The highest weight is apparently 35 or so. And now I have all the points here with weights. So they're still generally in that region. But these weights are, this is my posterior. That's kind of your thing you want to analyze. And it's a little hard to see how much yellows there is. This is a very short run. It hasn't been converged. Okay, it's not complete. It's just to be able to run it. But these weights are the thing you want. Now, do you want this plot? No, you don't. Now, the key thing, you want to find 68, 96, 90, sorry, it should be 95 percentiles of the weights. That is, this weight, if you think about this weight as an array, you want to not take the percentile. You don't want percentile of the array. If you do NumPy percentile, you won't get the right thing, because NumPy percentile is kind of finding the middle element, that there are equal number, say at 50%, it's equal number below above. You want to have weighted version of that. So if the biggest weight is 30, you say, okay, 30 plus, there are 10 of them that are 29, and then there are 18 of them that are 28. You add up until you hit half of the full sum of weights. And not half, actually 68%, right? And that's gonna be your 1 sigma contour. That's gonna be 68% confidence contour. I haven't coded it up here. I didn't find a very short snippet of code that can do that. But this, I highly suggest this as an optional homework for you. So you have everything. Here's your weights array. Your weights is just literally an array of numbers, right? It's if I have 10,000 steps, how many models maybe you went through? Oh, acceptance rate is 20%, right? So that means you had 2,000 models, 20% of 10,000. And so you have 2,000 weights. Rank order them. And you can do this in a slow way. Start adding highest number to lower until you get 68% of the sum. Union of those points, it's going to be some union. It's going to look like this, some union is going to be your 68% contour. Then you continue running the sum to 95.4%. That's going to be your 95% contour to sigma. That is the really, really important point of MCMC. That contour will be very jagged. Why? Number one, I don't have a lot of steps. Number two, people usually do a sneaky thing, they smooth their contour. So they have a very jagged contour, but they smooth it just because there's noise in this whole process, and you don't want to think too much about error on the error, right? You want to smooth it, and then it's good to go. Okay, let me see if there are any questions about that. Yeah, so that point, Matteo, omega matter is, yeah, I have a single point with chain omega. Oh, I don't have a single, so that's some kind of mistake. I don't know what this is. I think that was my very first maybe point or something. This probably didn't, there's no way this point was accepted. This must be a horrible fit. So I would have thought it's a speck on my screen, but it's not, it's a real point. I don't know what happened there. That's maybe I started there. I don't know. But how I get this one? Well, apparently that's not a terrible model to the data. Apparently that was accepted at least one. It doesn't appear to have a very large weight, but it's a very good question. How come some of these points are good fits? Are they really good fits? So what I suggest you do is you take one of these points and say, really, that wasn't a horrible fit. You take that model and just as a lig weight, I calculate its chi-squared. And then their chi-squareds are here. So you can see that point has a chi-squared. I have to look at this color now. So it's some shade of green. So it's minus 23. So this times 2, if I do take negative, it's like chi-squared of 50. So it's not a horrible fit. It's just supernova data. Remember, it's very degenerate in this direction, going from lower left to top right. So I'm not super surprised that that's a good, but this is the kind of thing that you have to scrutinize. You say, really, this was a good fit? And then you do it, and then you say, yeah, I guess it's not a horrible fit. And here, this is a good question, what happened here? I'm not sure. Okay. Yeah, dummy. Yeah, that's right. That was initialization, probably that point. Yes, thank you. Okay, and now how can you improve efficiency of this walk? Well, say you have a very long and thin posterior. So oftentimes you have this, if you imagine the final contour here, not this one, but whatever, the right version of this. Here it's a bit bulky, but especially as you go to multiple dimensions, they tend to be skinny and curved and bananas. They're not round balls, right? Typically, they tend to, and if there's degeneracy, God forbid, or pretty high degeneracy, you have a very long and skinny thing, right? And in 2D, it can happen a lot. In 10D, it happens all the time. You're going to have the volume that your contour will span will be very, very small fraction of the, if you take the projections to each parameter and multiply. It's really kind of a skinny ellipse, like a snake going through that space. That's how you think about these. So the way I'm stepping now, remember how I'm stepping, where's my stepping? The stepping was completely, it was P is P plus random number of this size in each direction. So pick a random number, Gaussian random on the X with this width, random number of the Y, random of the Z. So it's a vector that's some value in X direction plus some in Y plus some in Z. Knows nothing about the diagonal nature of this. So imagine if I had just imagine I have a very skinny thing. I'm trying to walk up and down and left and right, and the thing is skinny. So I'm trying to kind of walk generally, right? I give a general, imagine I have a skinny thing and I'm trying to walk. I'm getting rejected a lot. I'm getting a lot of rejections. We didn't see it in this problem because we only have 3 parameters and it's kind of well behaved, but you are getting rejected all the time. Imagine you have a snake and you're trying to make random, most directions are just going away from the snake, right? So they're going bad. So you wanna step in the direction along the major axis on the ellipse with a bigger step and along the shorter directions of the ellipse of the small. So imagine this is the ellipse. I hope you can see my cursor. I want stepping to be preferentially big steps here and preferentially small steps like this. And you'll be stepping everywhere, but so the way to do that, this is the final kind of a pro level exercise that you can enable yourself. You first run your chain for like 10,000 steps or some smaller number. And after you're done, say after you're done with this run, just say, give me covariance matrix of this, okay? Just covariance matrix of omega, meta, omega, lambda, and maybe script m. Then take the posterior covariance matrix of where you are after some number of steps. Then Cholesky decompose it. And then do Cholesky at this ampersand sign R, where R is Gaussian random. So basically, this is a math language for find the eigenvectors of this ellipsoid, of covariance being ellipsoid, and step in the one eigenvector in the other eigenvector direction. So make that your basis, and that's kind of a thing that you can also enable, not too much work. And now what you will see is your because acceptance rates tend to kind of fall to very low numbers. You'll see it go back up after you do this. This is all I have for MCMC. Any questions, and feel free to speak up as well. I'll take a minute here to answer questions, then I'll turn to something different.
Hello.
Yes.
Hi, Professor. I wanted to ask why it did not matter that we use the log likelihood instead of the actual probabilities during the MCMC.
Because you have
what if I, yeah.
That's easy. You have some inequality, yeah. And if you take log of everything, it's still inequality. So if x is greater than y, then log x is greater than log y. That's all I need.
Okay.
But
okay.
why you are saying why even go to log? Because likelihood has an exponent, and exponents can sometimes kill you if you take e to the minus 200 or e to the plus 200. They're dangerous exponents. If we don't like that danger to be blowing up.
Okay.
That's the thing that kills us. I don't know how Python. I'm a lifelong C programmer, so I know this can kill you. In Python, I don't know if Python is smart not to, but yeah, you're dealing with huge variation of that exponent, and so you just take a log in order to temper it down. That's what we do a lot in cosmology.
Yeah, understood. Thank you.
Yeah, it's a good question. All right, well, I don't see any other hands or questions. I'll move on, and you can still ask questions about this. I don't mind. So this is, okay, MCMC. Now, if I do this, can you see my exercise 4 slide? Can somebody give me a yes or no?
Yes.
Okay, thank you. Thank you. Super.
Yes, sir, just zone it a little.
Okay, I assume that was a confirmation. If not, let me know. Thank you all. So sorry, was that a no or yes? Now I'm confused. Can you see exercise 4 Hilpix?
Yes, just zoom a little to.
Oh, zoom in. Oh, okay. Because zoom is
Yes.
also the device we use. Okay, sorry. Yes. When you said just zoom, I thought you just see the Zoom app. Okay. Well, here we are. So sorry, as I was complaining at the beginning, this thing is a pain. Every other time it tells me it can't find my Hilpix. And I know Min over there, if he's listening to this, he's rolling his eyes. I must have done something suboptimally. But here's one recipe, how it works. For sure, this pip3 command, and you can run it out of Python by doing exclamation mark or like this. This can load you, and this is a kind of, here's why I installed it, but then it tells me it's skipping because it's installed already. So this is some mumbo jumbo just to get it to work. I'm not going to spend much time on this because honestly, I'm really no expert on this, and I just Chandra, I'm not sure in a Python environment. So this is why I suggest, that's why I have it. So first you run this line, it tells you whether you have it or don't have it, and then if it's not recognizing that, you can run this line. Also, you can just run this whole box with this line as well. That's the best. That's why I have these lines. You can just uncomment them. And if none of that works, then I don't know, then we are off to so the first line shows if you have it, you can do that first. And if it says you don't, then you install the second line. If it says you do have it, then this should just work. But like I said, no guarantees. Okay, so here, I ran it first, and now it wants me to do Hilpix map. So I go to it gave me this choose file as it did last time. So I'm going to do this Hilpix map. It's 12 megabytes, but it's behaving like it's 12 gigabytes. It's going percent by percent now. Okay. So while I'm waiting for that, and maybe you can click on that and wait, it takes a couple of minutes. I will stop sharing. I will do one more thing here. I'll start sharing. Oh, I probably could have just switched. Sorry, I should have. It was a matter of just switching window. So I want to talk a little bit about Hilpix, but before I do that, let me ask this. How many people have heard of Hilpix at all prior to this? Can you maybe raise hand? So the raise hand button should be there. How many? Let me see if I can just wait with that. Yes, close this. Heard of Hilpix before this. So I'm counting, I'm going to do like an optical count here. I'm counting. I'm counting ballpark 20 out of a ballpark 100. So 20%. Okay, good. Most people haven't heard of Hilpix. Hilpix is one of the great inventions of humanity. Thank you, everyone. Along with, basketball and okay. So here's a Hilpix. It's a way to pixelize a sphere. And so, okay, so you should be able to see the Hilpix screen. You can Google Hilpix. It has a Wikipedia page. It's a way that cosmologists invented in the late 90s to, if you think about covering a sphere in squares, it won't work. In triangles, it won't quite work. It can work, but you have to find them different. So you can put different shapes. Like you want one, sphere is famously hard to pixelate, right? Sheet of paper is easy, sphere is hard. It's a curved space, right? And there's lots of math terms. So this is a way that it's pixelized a sphere that has three very important properties. First, the pixels look like this. Every diamond is a pixel, and they're different resolutions. So there are some very nice properties of this. First of all, at any given resolution, you pick a resolution, every diamond has the same area. So every diamond, every pixel has exactly the same area, okay? Second of all, it's hierarchical. That means you can, and same area, by the way, is very nice. Hierarchical means you can split it in 4. So here, this one dark pixel was split in 4, was split in like 16, or maybe 32. So it's always powers of 2. So split in 4, in 8, I think. So you can split it finer and finer. So the old pixel just splits into new pixel. There's no kind of leaking. So that's another nice property. And the third nice property is it's isolatitude. That is to say, you have pixels that are going around the same latitude of a sphere, which is also very nice. So this is a super, super nice thing. And along with HILPix come whole software. This thing is ideal it's absolutely essential for analyzing CNB maps. It's also really useful for large-scale structure maps. I've used HILPix a lot in my research on CNB. And it's really easy to use. It's one of those things that you must have, okay, that if you use, and for large scale structure, also super useful. Now, let me show a couple more things here. So here's, you click on this and you have the so-called facilities here. So, IDL is this old, I used to be an IDL user, now it's Python, but if I click, you used to click and then all these commands are shown here, but nowadays I'm not supposed to do that. I'm supposed to click on HealPy. And so HealPy is the Python version of HILPix. It used to be C or Fortnite Python. So it has a lot of nice, so first of all, before I look at that, sorry, I want to do one more thing. I want to look at this. This is a document, This primer is kind of essential document. And HILPix, this is, if you unroll the map, this is showing you the math of this. But if you unroll the map, it looks like this. Now, this is how kind of roughly version unrolled. Of course, if you unroll the sphere, then all of them look the wrong shape. So this is kind of artificial unrolling of the sphere. And the number here at certain resolution, there's the numbers of the counts. But there are unfortunately two ways. Unfortunately, I say because it makes it a bit confusing. There are two ways to enumerate this. One is called nested, one is called ring. So there are two, you have to pick one, a ring or nested, and you can see the difference is, I forget which one is which. One starts with 0, 1, 2, 3, these pixels on the North Pole. And for the other one, their numbers actually 3, 7, 11, and 15, because the numbering goes differently. So there are two numbering systems, but they are physically and mathematically the same. They cover the same. Okay, so you have to know if it's ring or nested. In our example today, it's all going to be nested. Okay, so you just have to pay attention to that. And then if you go to HILPy, you can see it has a lot of nice things. There's a tutorial, etc. But here are some of the key functions. Pixel functions are, for any given pixel, you can find angle, like theta and phi. So you can give pix to angles from pixel number to angle, or you can go ang to pix. From angle, you can tell me what pixel, and then you'll tell you the pixel number. You can say pix to vec and vec to pix. So you can give a vector, x, y, z coordinates of a vector starting from the center of the sphere for pixel number and vice versa. And then you can do a lot of similar things. Like I said, the resolution is given by the n_side, and n side is a power of 2. So n side is a resolution. It can be 2, 4, 8, 16, 32, etc. to 4000. And the rule of thumb is that n side of 60 is about 1 degree. So n side of 64 is 1 degree pixels. N side of 128 is 1/2 degree pixels. So when Kobe came out, you only need like a low n side for it to look good. But with Planck, you need n side of 2048 or 4096, which are high powers of 2, which corresponds to, I don't know, a few arc minutes pixels. Okay, and then the other set of functions is these golden functions, and these two are most useful, ANAFAST and SYNFAST. ANAFAST, you give it a map, it'll give you the angular power spectrum, just like that. And SYNFAST, you give it the angular power spectrum, you give CLs, say produced, for example, from CAMB or some other way, it'll give you the map. Let me stop here. Okay, so some people already know a lot about this, I see. Some people are showing off their knowledge of this, very good. But let me see, are there any like basic questions? Okay, basic questions, what am I talking about? Why are we doing this? Why do I care? Why couldn't I just do this myself? Why do I need HILPix? Any basic questions? I'm happy to hear those. The magic wand, yes, it is. But I mean, I don't suppose everyone's immediately convinced. So I just want to see if there are any basic. Okay, I hope you can see this back to exercise 4. If not, then somebody speak up, but I hope you can see this. So now it loaded this Planck map finally. I'm gonna run these boxes slowly. And yeah, I need the style file again. because I tied myself into making pretty plots. Okay, so now we start with HealPy. So I loaded up HealPy, and it's hp.command, right? HealPix command. So these are read map. I read this map, and okay, I can click that. It's gonna read the map. It gave some warnings, but I can ignore it, says here, okay. So the function above should also print nside. That's resolution map. So nside is 512. This is kind of in the header. So 512, that means it's about what? It's bigger, 8 times bigger than 64. So I think I'm saying that here. So the pixel is about 1/8 of a degree, because remember, nside of 64 is about a degree pixels. So it's 8 arc-minute pixels. If it means something to you, that's going to be my resolution for this blank, okay? And because I need this, I'm going to explicitly define inside parameter just because I'm going to need it. I don't want to, you know, I'm just going to define it here. And all right, so use function HealPy MolView to display. So I think I'm actually not asking you to do anything here. So MolView is one of the representations. It's like Mercator projection. It's one of the projections for a sphere that we can see it on a piece of paper. I'm calling this CNB_map. That's important to remember. I'm going to label it nicely, and I'm going to say units are Kelvin, because maybe this even told me units are Kelvin. I don't know if this. Ordering is ring. So hopefully ordering ring or nested. Remember those two orderings, they always get to me, but hopefully it won't this time. So this is going to be a big moment. And this is out of the box. You should be getting this. It doesn't look right. It looks not right. Okay. Yes. Answering questions. Enc to pix. Do you give it set of angular coordinates? You can give it one set of, you can just give it theta and phi. You can even specify degrees or radians. It'll tell you pixel value. Of course, you have to be specialized all along in the ring or nested convention, right? But that's not so hard to do. And I'll tell you one thing, if you mix up these conventions, ring or nested, and plot a map, it'll look horrible. It'll look totally not like the universe. So that's the moment you say you mixed up the convention. So it's not very hard to figure out. But yes, outside of that, you just give it angles, Matteo, and you get. That's Luan. That's a very open-ended question about machine learning. I'm not sure. Maybe we can leave it for later. That's very open. Yes, homogeneous universe. Yes, Vincent Luan. Okay, yes, Mariana, you have a good question. It's coming up what I'm going to talk about. So let me just postpone. And please remember to ask again. Yes, that's an important question. But here, for the moment, I have a more burning issue. I had this nice thing, Kelvins. It looks horrible. What happened was something was wrong. And you can, if you look at the Kelvins here, it's a pretty big scale in Kelvins. Remember, anisotropy is like 10 to the minus 5, right? Kelvins. So the core of the galaxy is so bright that, you know, the maximum temperature was very high and the minimum temperature was very low because I have some stars here. So the stars at the center just expanded my scale, right? The brightest and the dimmest thing in the middle expanded my scale, and now I can see the real thing outside. The galactic plane, this is galactic coordinates, so galactic plane is here. So I have to fix this up. So first, fix up places, I'm asking you to fill this out. Same command, but min and max are for you to fill out. So I just need you to fill out two numbers. So you can play with this. You can play with this, and I'm gonna cheat a little bit as usual. You can play with this. And you know, if you can, well, let me play with this. Let me do 2 zeros and 3. Max is 2 and min is minus 2 point. So this is like 100 times less. It should look better. It looks okay. Now I can see what the culprit is, the center, because this is where the really high so it's saturated at the highest and lowest pixel in the center. But if I do it still 10 times more, I'm going to oversaturate the center and I'm going to bring resolution out. So here I should be getting beautiful, the face of God, you know. Yeah, so that's the map of the real CMB. You can see the large structures, the small structures, and you can see this oversaturated, very thin. This is not the full galaxy. This is after a bunch of cleaning, but in this particular map, there's something left over. You can see it by eye, okay? But at least we now have a map that looks really nice. Yeah, that's right. And you can, if you chose different numbers, that's fine too. All right, good. So now find coordinates just for fun of the brightest point in the map. So first you have to, what's max pix is, and now you have these commands, find the maximum pixel of np mac argmax of, well, the only thing we have at hand is CNB map. This is the only like array we have so far. So that should hopefully be good. And then coordinates are, and I'm really saying how many degrees longitude and latitude. So now this is the case where you have to go to that website and look up these commands a little bit. So it's hilpix dot, and then it's literally, it's either pix to ang or ang to pix. Here I have the pixel number, so it's pix to ang. And for pix to ang, and this thing is super smart, you have to give nside, which I gave. You have to give pixel number, which I found as max pix, that's the thing above. And then nest is false is a default, and I think it told me upstairs I'm in the ring convention, so I'm good. Remember, there are two conventions, so I think I'm good on that. But in this code, I want to say longitude and latitude. I want to get in longitude and latitude. I forget what the default is, but if I do this, it's going to give me longitude and latitude. Run that. So coordinates are 200 degrees longitude and minus 90 degrees latitude. Now, this is the case where, okay, I have like 50% chance of saying something silly, but it should be, the maximum temperature should be in the middle, right? Right here in the contaminated region. And if I know my longitudes and latitude, latitude is one going up and down, and I think 0 is in the galactic plane exactly. So 20 degrees is not too far. So it's not, I hope I'm getting that right. I think that's right, 20 degrees. This is one that kind of goes in a azimuthal direction. This is one that goes in the theta direction, so to speak. So that looks about right. All right, let me stop for questions. We have negative K because these are, yes, thank you, good question. These are perturbations around 2.725 Kelvin. These are fluctuations. So this is really delta K. We got used to this so much role that we don't even pay attention to say it. You know, sometimes you see, if you show the absolute temperature, it will be tiny fluctuations around 2.725. So you wouldn't see it by eye. So you want to subtract the mean. We subtract the monopole for the most part. And then you're looking at fluctuations. So you have fluctuations up and down around 2.725. Yes, thank you. Somebody answered that. Yep. Right, it gives coordinates of the center of the pixel, which for small pixel isn't important, but here, yes, it's center of the pixel. You can get area of the pixel, you can get neighbors to any given pixel. And imagine if you're coding on your own and even if you pixelize this sphere, you sweat it a lot, I don't know, for PhD, and then somebody said, well, what are the neighbors of that pixel? What are the neighboring pixels? And that's a job to do, and here you have commands that give you this kind of thing. Okay, so that's very nice. Now we do for the real things. Now we want the famous angular power spectrum. Now, if you're a cosmology student, I know I haven't introduced it, but you probably have heard of angular power spectrum. It's the equivalent of the power spectrum of 3D, is angular power spectrum. It has all information about angular power in a survey. You can do it for the CNB. You can do it for large-scale structure too. If you take angular picture of large-scale structure, you can compute its angular power spectrum. So here I want you to do, so this exercise is not from scratch, if you noticed. You could do this from scratch, but here it's really much better to do HealPy Anafast. It's going to be one line of code. Otherwise, because you have a full sky, then delta T over T is expanded in sum of ALM, YLM, right? So ALM are the coefficients, and so by orthogonality condition, you can write that ALM coefficients with the complex numbers is integral delta T over T of n hat, YLM of n hat, and it should be YLM star of n hat. It should be YLM star. That was a typo. So let me see if I can get back to, how do you close this? Okay, right. So this is the expression delta T over T, YLM star. This is the integral you do. And then you calculate CL from the definition we have. So these LMs are sometimes called the phases. They are coefficients that describe the temperature map. You have to do this operation. You can do it yourself. You can do it in HealPix. It's easier. the area of each pixel is the same. This dramatically simplifies, right? So this, for example, goes right in front of the integral. It's just a sum. And why, you can get YLMs in Hilpix. You can do this without Hilpix also if you want. And you can do CLs as equal to this is definition. ALMs are complex numbers because even though delta T over T is real, YLM, of course, is a complex number, as you know from mathematics. So these are complex numbers. The absolute value squares are real. This is real. You can do it that way. The problem with doing it this way is what Mariana raised, that unless if you have a full sky, and you almost never have a full sky, even Planck doesn't have a full sky because you saw that problem in the middle, then ALMs are very highly coupled, and they are actually really hard to extract the phases. Angular power spectrum is much easier than ALM. In large scale structure, this is the same as saying as power spectrum P of K is much easier to get than over density delta as a functional position. If you have to imagine, I give you some survey and I say, here's dark energy survey data, just give me the dark matter over density as a function of. That's really, really hard, like impossible. There isn't enough information. But power spectrum is this average, and because you're doing a bunch of averaging, you can get it. But because this procedure, it goes through definition of ALM and CL versus ALM. It goes through definition, but it's super, not just inefficient, it'll give you answer that's unstable, it blows up one way or the other, because you're going through the quantity here that's very unstable. So you want to get directly to CLs. I hope that makes sense. And that starts the answer to Mariana's question, what if you have a cut sky? You don't do it this way, okay? You do it this way once as a grad student and learn that was a bad mistake, okay? It won't work. Another way to do it is kind of weird. You have CL, which is like P of K in large scale structure, and you have C of theta, which is like psi of R in large scale structure. It's angular two-point correlation function, which is pretty easy to get even on a cut sky. And because it's real space, most humans have an easier time understanding real space than harmonic space. You get this quantity, and then you integrate it just like this. You literally do this mathematical integral to get CL. But this is known as a suboptimal method mathematically, but I kind of like it. It's very intuitive. Pedagogically, it's good to know about. But ANAFAST is just a code that we're going to do full sky, so it's going to be good. When you start cutting the sky, you have to start paying attention. Okay, so I run this ANAFAST, abracadabra, and well, it's just not going to do anything. It's just going to say it's happy. Yep. And then I want to plot not CL versus L, but this quantity you always see LL plus 1 CL over 2 pi, which we call DL. So I want you fill out a few things. So L is, first I'm going to help you by saying this is array of L's, and however many CLs I have that ANAFAST returned, L's are going to go from 1. I happen to know that these start at L of, and maybe they start at L of 0 and these start at L of, I'm going to start at 0. So if I got 1,500 CLs, that means L should go from 0 to 1,499. And that's what this command will give me. Okay. I'm asking you to fill this out and that out. And while you're doing that, I'll take a look at the chat. ANAFAST, that's a good question, Matteo. I think, I actually think it does, I'm not sure. I think it does that naive method through ALMs that I said don't use. Because I know you can't use ANAFAST. Well, we're going to run ANAFAST and see what it gives us, okay? But I think it uses the method I say is not the greatest idea. It just does it efficiently. So you really have to massage it a little more if you want to do it right. Well, Matteo, you just got to the edge of my knowledge on ANAFAST. I think it uses the naive method. You certainly can do just ANAFAST for professional purpose. All right, so these are pretty easy lines of code. It's not like the thing yesterday where, so prefactor, how am I calling it in my code? F prefactor is L times, when you multiply arrays in Python, it does it piecewise multiplication. So even though this is an array, L to L plus 1, each element is going to be multiplied piecewise. So okay, this is just that. And then multiply again piecewise, DL array is going to be just F times CL. This is amazing how simple it is. It's piecewise, so it's going to be LL plus 1 CL for at every L, it's going to do that for me. So it's almost like unfairly. And then I'm asking you to do this. It's really nothing. It's plt.plot of L and DL. So DL versus L. Yep, that's all. And this is a big moment in a lifetime of cosmologist. Here's the angular power spectrum. Does it look right? Does it look right? This will be like the ugliest ever power spectrum obtained. I mean, no, it looked completely wrong. There's nothing familiar about this power spectrum. You say to yourself right away, wait, should I have multiplied by LL plus 1 because this is going with L? Yes, you should have, because the thing shown always L is this DL. It's I labeled it with units, it's LL plus 1 CL over 2 pi. So that part is right. So I'm telling you, if I got this, I'd be immediately looking for a bug here. But now I'm telling you everything is right. So what went wrong? Well, looks wrong. The bright core of the galaxy is a big contaminant, okay? So core of the galaxy is just adding a ton of power. Remember that it's thin, but it's messing up everything. So here, I'm asking you to do this, and here's where you do a little bit, you have to go and look up, but plt.plot of galaxy cut, right? So no, I don't plot yet. I do it CL is equal to hp.anafast of CNB map. This is what we had before, but now I add gal underscore cut. Flat galaxy cut is 10 degrees. It knows it's degrees somehow. But because I went back to the CL, I have to repeat that this is CL. I have to repeat this. I don't have to repeat F. F has already been memorized, but DL is going to be different because CL is different. And then I need plt.plot of L and DL. So these commands are the same. This is the only new thing. So I just made a flat galaxy. What's 10 degrees? 10 degrees is, remember, they're 90 degrees to the North Pole. This means plus minus 10, by the way. So that was a pretty thin thing, so it should be okay. So I do that. I hope for the better result. And it should be better in a moment. And so it looks better. This looks better. The amplitude is, by the way, 10 to the minus 9. Oh, but my units are right. Wrong. You can see my units are wrong, because if this is 10 to the minus 9, then this was kelvins, right? So I got the wrong units immediately in the label. But otherwise, I see the first peak. That looks about right. And then I see this thing just doesn't look right at all. But this gives me hope that something right is going on here. Well, that's a little better. But now what happens is in the CL, so once you get experience with CLs, there's a shot noise in this procedure. It turns out that there may be some low-level noise. And if you think about the CLs, remember what's shown here is like L squared CL. So this goes as L squared. But if I plot this, just CLs are maybe falling down, right? CLs are, I don't know what they're doing, but they're slowly petering down. And if I imagine, it turns out that white noise, just random noise, that's, for example, due to point sources or other, it is flat in CL. So this is a good rule of thumb for those of you who ever touch, well, large-scale structure CMB. White noise corresponds to CL over constant. This you can prove. So there's a white noise, there's a flat thing in CL, not in DL, that's messing me up, and it's basically adding power because CL is falling, it's destroying high L of the CL, and then as I multiply by this LL plus 1, it looks like it's a raising tail. So, and I happen to know, a little bird told me that this is about the level of noise in the CL. So I'm asking you to do several lines of coding here where you fix this up and just subtract the noise, but notice you need to subtract it from the CL, not from the DL. You can do that as I look at the chat. So noise is flat in CL, Reggie, flat in CL, but CL is falling with scale, so it hits higher Ls more. If it's white noise, it's CL constant floor. Yep, that's what happens. And this literally little bird told me, I don't know that I would have immediately thought of this, but so, well, several lines here. So, well, we don't need to do a whole lot. We just say CL is going to be equal to CL minus whatever this minus 2.1 e to the minus 14. So we're going to fix it up like that. Oh, and I call that CL noise in my solutions, whatever. And then dp dl is equal to f times CL. I repeat that. And then I plot that. So I think that's all I need to do, just subtract, but I have to subtract and then recompute the DL, right? Don't forget to recompute the DL and to do this operation CL. If I do that, oh la la. So now I have a big moment in a life of a cosmologist. I analyzed the real map using some tools, yes, and I got angular power spectrum that's starting to look quite right. It has the peak about the right spot. It's a L of about 200. It doesn't quite look right here, but I'm going to smooth it in a moment and see how it looks. So a couple of things here. So first of all, let's marvel at this. What do we have? We have at every multipole. So NFS gives me this at every multipole. Maybe I should have told it not to try too hard, to do every 5 multiples or every 3 multiples. And sure, I can smooth this. I'm going to smooth this in the moment and get it to be more accurate. But doing a really fine thing and smoothing isn't optimal. You really want to say, okay, I don't quite have the full scale. Let me do every other multiple or something. I'm going to get a more accurate result. Okay, that's the thing number one. Thing number two, this I'm supposed to see second, third peak here. I'm definitely not seeing it. And notice I have a linear scale. Had I had a log scale, I hopefully would have been able to see a Sachs-Wolf Plaftor here, but because I have a linear scale. The amplitude, so my units have been wrong all along. But other than that, as I just discovered as I'm speaking, because this should be, if I'm in Kelvin, then this number is looking much more logical. Bispectrum Esteban, remember that question, I'll tell you. And 1 times 10 to the minus 8 is which, referring to which part, Mariana?
Oh, the amplitude consistently I've been getting 1 to the minus 8 instead of 1 to the minus 9. I thought.
Does the shape look like this?
Yes. Everything is identical. So
but the numbers are really different. So the maximum isn't 5 times 10 to the minus 9. Okay.
Yeah.
Oh, okay. I do have one idea. So one, so this is a veteran's suspicion here, but I'm not sure it's right. You ask yourself, well, if I'm wrong, I'm going to be wrong by like 10 orders of magnitude. Why would I be wrong by a factor of 5 or 7 or something? Sometimes there's a confusion if it's delta T over T or just delta T, because T on the bottom is 3 Kelvin, right? So if you do work in Kelvin, it's 3. So in the power spectrum, it's 3 squared. It's like 9, right? So there's a factor of about 10, a factor of 9, whether it's delta T over T, which is dimensionless, or delta T, which is in Kelvin. And the difference is, again, that factor of just temperature squared, and temperature just happens to be like a small number, like 3. So how could they have gotten wrong? You have to go way back and see, because you have the same map. This probably didn't matter. So at which point do you tell it if it's delta T or T? I don't know actually how. I don't know if you potentially inserted some command. I'll be curious later to have a quick look at your code. Maybe if you inserted some place where you tell it if it's one thing or another. It should, because all of these are just straight up math commands. So I don't see how it could have percolated. Well, that's a really interesting bug. But I'm telling you, if factor of a few is often that confusion I talked about, which I've hit many times. Okay. So very good question, Mariana. We'll get to the bottom of that. And yeah, one more thing. First of all, we are plotting these multiples too high. I think this thing goes to 3 n side minus 1. So everything is dependent on n side. As you go, if you want smaller scales, you want to go to higher n side. Of course, there's no sense going to very high n side if you have a coarse resolution map. But this being Planck, it's a pretty good resolution map. N side of 512 is not extracting all Planck information, but it's okay. So, but it turns out, if you study the math of this, you can only be accurate at all up to 2 n side. After that, it's garbage. But this went to 3 times n side. So it's only good to about 1,000 for us, and we went to 1,500. So don't make a plot going up to this value. You can do this couple of ways. You can do I'm just going to do it by limiting the range here. You can also go back. The more proper thing would be to go back and change when you do run unfast, impose the limit on this kind of limit. So that'd be a better way, but I'd have to rerun code. I'm going to get the same results. I'm going to do a lazy thing and just chop off the graph at 2 inside. So my maximum x is going to be 2 times inside. The other thing is to smooth, and here I'm providing a smoothing function. One of them is called Savitsky-Golay filter. This is, again, a kind of thing that in Python is so easy, and if you do something else it's not so easy, you have to do more coding. But I'm going to smooth with a window that's delta L of 20 and third order polynomial. So I'm going to get a smoother function. I do that smoothing, I get a smoother thing, and I'm only got out of 1,000. Again, I should have really redone the unfast thing, but it's okay. This doesn't look quite right. Why not? Well, because one has to put more effort to get this right. That's why. So you can only, on the cheap, you can get quick main features of the CNB, but as you go, especially to smaller L's, you need a little bit more care, and a lot of them have to do with Mariana's original question, well, what about the cut sky? Cut sky is a big pain. If only we only ever dealt with full sky. Because if you think about estimator, there are many estimators for CL, and people talk about optimal estimators. All of them agree on the full sky. You can't go wrong on a full sky. Everybody is mathematically guaranteed to get the right answer. It's just when you have a cut sky map, and like I said, even WMAP and Planck have cut sky map, but if you go to large scale structure, you have a smaller map. If you go to previous CNB surveys, they were covering small patches of the sky, 5 square degrees. 10 square, 100 square degrees out of 42,000 square degrees in the sky. So you always have very heavily cut sky, very small chunk. And then getting these higher L details, it requires care. And it's well beyond the scope of this lecture, okay? You have to worry about edge effects. This comes from the same fact. If you take a sharp function, we had a top hat spherical function in my lecture as an example, but if you take just any sharp function in mathematics and take Fourier transforms, what happens? You get infinitely many Fourier components, and they're all large. They're kind of positive and negative large because they're canceling out like crazy to trying to get the sharp edge of the function, right? So here, it doesn't have to be sharp. You can say, well, I have only a finite area. Let me not make it smart. Let me apodize it. Let me make it smoothly go to 0. So you can start playing those games. And at that point, you're doing advanced graduate work, right? It's a real non-trivial thing. So this is actually kind of hard to get right. But you can see that we got the first peak, and we got the real CNB power spectrum. We are very satisfied with this. And as an optional things, you can do a whole bunch of things. Many of them are very easy. They are one-line commands. You can remove monopole and remove dipole from the map that they are hp.remove_monopole. So they're very easy commands. Sometimes monopole is removed for you, sometimes it isn't. Oftentimes when you see galaxy, even then I think it depends, it isn't removed. But we remove monopole and remove dipole, but immediately there are questions. If you look at that map, right? If this was just a beautiful CNB map, you would, first of all, monopole would have been already subtracted. But this is the weird thing. You have a galaxy. So if you subtract the monopole, because these pixels are more often positive than negative, you can get, so you really have to worry about, does it commute to cut out the center and remove monopole? Do I first remove monopole and then cut out the galaxy? Or do I first cut out the galaxy and remove the monopole? Okay. Again, this is more advanced graduate work. This is not baby stuff. Yeah. You start worrying about things like that. But anyway, if this is why you need human brain to do this. Hillpix will make it easy for you to remove monopole, but of which stage? You can remove dipole. This is a really fun thing that I'm not going to get to, but you can degrade map to a coarser resolution. So you go to one of these higher inside resolutions, Hillpix to lower. You can do it vice versa. So this is really fun. It should give you the same power spectrum at large scales, and the power spectra should differ a lot at smaller scales than the coarser resolution. This is a really fundamental thing to generate a CNB power spectrum. So you feed it angular power spectrum, say from CAM, and you run SynFast, and voila, you get a map. Now, it'll pick phases for you randomly. It'll pick cold and hotspots for you randomly. It'll just be consistent with the same power. if you give it just the CLs. But if you give it the ALMs, then you gave it all information. That it will literally give you the hot and cold everywhere as you want it, right? So if you just specify the angular power spectrum, which is what often you want, it'll just give you a random realization that's consistent with that power. So for example, sometimes cold spot will be on the North Pole, sometimes hot spot will be at the North Pole, but the overall power spectrum will be consistent with that CL. Or you can just generate random up. You don't need chem for this here. You need a chem here. You can just say, go up in the code and just say CL is constant and run synfast. It's like 2 lines of code and you get a map. Look at it. You can look at it and ask yourself, does this look like the CNB map that hangs in my department's hallway? It shouldn't. Something is going to be off about it. It shouldn't look like white noise. And then, of course, you can calculate angular power spectrum. You can do it with Hilpix. I think you can also do it yourself. You can even do simple counting pairs, and then you can convert from that to CL. You can compare. So this is a lot of kind of fun exercises. What I like about this is it's fairly easy. I always like easy things, and this is undergraduates in my group have even written papers on this, but they've definitely played with Hilpix a lot. It's something that one can pick up and do with no sweat. So it's a really it's good for CNB, for large scale structure, for potentially particle astrophysics. If you need map of anything, map on the sky, I think you want to go through Hilpix. So let me actually stop there and maybe continue with some questions now. So this is the end of the official lecture. Maybe I stop sharing screen.
Well, thanks a lot, Dragan. Well, we'll have questions now, and then we finish we finish the school in a second.
Yeah, well, I knew we were also talking about question answer session now. Well, I can go with this one question. I say Javier asks, can we generate CNB maps? Yeah, so there are some questions about non-Gaussianity type things. And if you want to put in non-Gaussianity, Javier, you kind of have to do it yourself. You can go through Hilpix, but you can't just run Anafast. So this is a kind of thing where you have to specify what kind of non-Gaussianity. It's actually not so easy. You can do it yourself, but first and foremost, you have to decide what kind of non-Gaussianity you're putting in and what. So it's not super straightforward. Somebody asked, can you measure the bypass spectrum? Not through Hilpix, as far as I know. It's another advanced task. It's not an easy measurement. Remember, power spectrum of anything has one number, P of K or C of L, and bispectrum has 3 numbers. So right there is a proliferation. So not easily. The answer to both questions is not easily. It's definitely doable, but it's like a mini research project just to get that going. Oh, there's a non-Gaussian simulation. Yep, that's right. Sarah, you're right. That's about right. It's publicly available, yes. So I still count that in the category as not completely trivial, but if somebody made it up out there, that certainly has happened. So very helpful, Sarah, thank you. Any other questions?
Well, people are completely satisfied, apparently. Sorry, somebody wants to ask a question there?
Yes, first, thank you very much for the course. It was really amazing. I would like to know if how long it will be available, all the scores and links for the Google Colab, for we can make training and make tests.
Well, I don't know Colab that well, but it's like Google Drive, so things stay there forever, and I don't intend to remove anything myself. So I'm gonna leave it there. You certainly feel free to contact me. I've created these exercises for this school, but it's like Google Drive, things sit there forever. Does that answer your question? I think they sit there forever, I'm not sure.
Yes, amazing. Thank you very much.
Yes, and I'm really glad to see these comments about removing fear, because that was exactly my point here. You know, it sounds like a scary thing. A lot of things sound scary in physics. Okay, theoretical, usually, sometimes numerical. But this, once you could start going through Hilpiks, this is really truly an undergrad level. The hardest part is downloading the damn thing, you know, or having it to be recognized. And once you do that, it is really, and you start opening and making these maps, and the ones that are wrong will look very wrong. So quickly, this is really one of the easier things in cosmology. Like the bang for the buck is big. You can really get ahead with doing some interesting stuff with Hilpiks. So this is when I work with undergraduate students, this is kind of my go-to direction to do something through Hilpiks. And of course, you can get it to do way higher things. You know, it's a very useful tool.
You're not getting too many questions, but you get lots of thank you so much and lots of praise here. Yeah, so it's wonderful when these things, you break the barrier.
Yeah, break the barrier. Yes, yes.
Anybody can do whatever they feel like.
Yeah. And then you start playing, you start digging, you learn more about the package, and then you feel much better about the whole thing. You know, then it's rolling. But starting it is, for me, downloading is usually the hardest part. It doesn't work. Why is it not recognized? Who can help me? Of course, nobody. So yeah.
And guys, I'm sure that you also, guys and girls and people of all kinds, you got each other there also. I mean, we realize how much you help each other also. And I'm sure that the school here had this effect of putting you guys in touch. Everybody can not only write to the lecturers, I'm entirely sure that they will be very happy to answer questions even after the school is over. We actually saw that some of the lectures from last week were answering on Slack on this week. So, you know, feel free to write to people. I'm sure they will be delighted to answer your questions. And you have this community of people that are interested in these things now that you can use for help. And let's finish again by, well, unless anybody has another question, last chance of this whole school, no? So let's everybody turn on the cameras and thank Dragan for the wonderful set of lectures and all the notebooks and exercises.
Thank you, guys. Thank you. Thank you. It's been such a pleasure.
Thank you very much.
Thank you all. Feel free to contact me. That's like, you know, I'm happy to answer questions.
Cool. And Rogério, just confirming, we will send those feedback forms for everybody very soon, right?
Yes. So Jandira should send the feedback forms for